Okay, so the second part of today's lesson, looking at related rates, but specifically in the context of parametric equations. So first thing I want you to do is take a second to warm up and use all the techniques you have to try and sketch the curve r equals a times 1 minus cos theta, where a is a positive constant, varying theta between 0 and 2 pi. So it's a polar form. You could substitute in some values. You could think about what happens to cos theta as theta grows between 0 and pi over 2, pi over 2 and pi, etc. However you want to do it, investigate this function, this curve, see if you can draw it. Pause the video, have a go. Okay, so here we are. This is the function, and here we have a being fixed. I can decrease or increase the value of a. All I see that happens to my curve here is that it increases or decreases in size. So this is called a cardioid, and we're going to come back to this idea later on. Cardioid is an important shape for a number of reasons, but perhaps easiest to understand is to do with microphones and speakers. You get it's really common to have cardioid microphones which pick up sound in shapes like this, in a cardioid. So if you speak to Mr. O'Sullivan about what types of microphones he has, one of the things he'll tell you is, yeah, I've got some cardioid microphones. We'll come back to the cardioid soon, but hopefully you've got something like this. If you start with theta being equal to 0, the radius is 0, and then as you increase theta to pi, the radius increases as well, and then as you move from pi back round again, the radius decreases. So we get the second half of the curve. When we get to 2 pi, we're back at the beginning with a radius of 0. So related rates and the chain rule allow us to investigate curves like this and to calculate the gradient of them, even though they're not functions. Let's have a look by turning to our notes. So that cardioid was an example of a parametric curve, and you did some work on this in the pre-work. They're specified by a pair of equations, x in terms of t and y in terms of t, a separate function. Examples of that would be the unit circle, so you could fill these in for yourself, but unit circle, the x-coordinate is cos t, the y-coordinate is sin t. A parabola, again we should remember this from our pre-work, even if we can't remember the exact form. The x-coordinate at squared, the y-coordinate 2at. And the cardioid, the one we just looked at there, writing small, a times 1 minus cos theta, and a times 1 minus cos theta, sin theta. And if we just think about the equation we looked at, the radius, well, that's the square root of x squared plus y squared, and as we do that, we see that we're going to get a cos squared and a sin squared. They're going to cancel out, leaving you just with a times 1 minus cos theta. So that seems to work. That's good. If we look at what the parameters are, well, often we call them t or theta, depending on whether we want to imply that we're talking about time or an angle. And irrespective of whether it's time or an angle, we remember that parametric equations, they give us a little bit of extra information than a Cartesian curve. And I like to think about it in terms of a comet, because quite often we're talking about ellipses and circles here. A Cartesian form for an ellipse gives you the path of the orbit of a comet that's moving around it. However, the parametric form gives you the exact coordinates of that comet at any particular point in time. And really that's the difference between the Cartesian form and the parametric form is that if the parameter is meaningful, if it means something like time or the angle, it gives us an extra bit of information and allows us to find the precise position, not just the overall path. So, parametric equations may contain more information than Cartesian equations. In other words, we could go the path of a comet or a satellite or something like that, whereas the parametric form tells us the location at time t of a comet. Okay, now the chain rule, just like we've been using for related rates, can actually help us find the gradient here, because the gradient dy by dx, well, using the chain rule, that must be the same thing as dy by dt times by dt by dx, which must be the same thing as dy by dt divided by dx by dt. And using the expressions we've got here, that would mean that it would be g dash over f dash. So parametric form actually gives us a really nice way of finding the gradient for a specific point. Just notice here that, often we're talking about circular orbital motion, things which are not one-to-one or many-to-one. And so they're not functions. However, we can still look at dy by dx for these things, and we can still do that with the cardioid that we were looking at earlier. So hopefully you recognize these equations for the next part. They go exactly with the parametric form of a cardioid. And what I'd like you to do is just pause the video and have a go at finding an expression for dy by dx for these parametric equations using the form we just looked at. If you've done that and that worked out well, try the one underneath, and I'll go through them both in a second. Just pause the video and have a go for yourself. Okay, so there's a bit of a formula for doing these, and I've chosen these two examples because there's just a little bit of algebra, a little bit of simplification to do as we move through. So I know I'm always going to be finding dx by dt and dy by dt. And then I'm going to put those together using the chain rule. But dx by dt, looking at this expression here, I'm going to do this by using the product rule. So I remember the product rule. It means differentiate the first, leave the second the same, leave the first the same, differentiate the second. So differentiating cos t first of all gives me minus sine t, and then I leave the second term the same. Then I add on the first term left the same times by the derivative of the second. And just being careful here, the derivative of minus cos is sine, so this is just cos t sine t. So in other words, as I simplify this, I've got 2 cos t sine t minus sine t, and we could leave it like that, but 2 cos t sine t, I can't resist here. I'm going to use the fact that I know that is the equation for sine 2t. So sine 2t minus sine t. And that's a nice neat form for dx by dt. Okay, dy by dt working a similar way. Well, using the product rule, cos t times 1 minus cos t plus sine t times sine t. That's going to give me cos t, and then minus cos squared plus sine squared. And this is interesting because here in this I can see the form for cos 2t, just like I used sine 2t before. So cos squared minus sine squared is cos 2t. So this is going to be overall cos t minus cos of 2t, using that identity, which means dy by dx in a nice neat form is going to be dy by dt divided by dx by dt. So it's going to be cos t minus cos 2t over sine 2t minus sine t. And I'm not going to waste your time doing it now, but what I'd like you to just spend a moment doing is look back at your sketch of the cardioid, or look back at the picture that we had before, and just think about the numerator and the denominator here. Satisfy yourself that you're getting zero gradients and undefined gradients, or asymptotes, not asymptotes, if you like, sorry, vertical tangents, where you're expecting them. So vertical tangents should occur when sine t equals sine 2t. Think about where that is. And we should have a horizontal tangent, or what would look like a maximum or a minimum, where cos t equals cos 2t. And I'd like you to think about where that would be, and just check that that fits with your cardioid. Otherwise, let's go on to the second example. So, same process as before. I'm going to find dx by dt, I'm going to find dy by dt, and then I'm going to use the fact that dy by dx is dy by dt divided by dx by dt. So that's my method each time. Dx by dt, well, 2 for differentiating 2t, and then minus log e of 2t, well that's going to be minus, using chain rule in my head, the derivative of the inside function times by the derivative of the outside function, with the inside function still in it, so 2 times 1 over 2t, or in other words, 2 minus 1 over t. The 2 and the 2 cancelling here. Dy by dt, 2t for the t squared, and then using the same idea, the chain rule in my head, differentiating the inner function giving me minus 2t, multiplied by the derivative of the outside function, so that's 1 over, with the inside function still there. So 2t minus 2 over t. Great. Just looking at these are the expressions I'm going to substitute in here, but because I'm doing a division, if I can write these as single fractions, that's going to help me out. So, writing it as a single fraction, I think dx by dt would be 2t minus 1 over t, and dy by dt is going to be 2t squared minus 2 over t. And then as I do this division here, I'm going to get 2t squared minus 2 over t divided by 2t minus 1 over t. Dividing fractions means find the reciprocal of the second and then multiply. So, in other words, 2t squared minus 2 over 2t minus 1. And there's my closed form expression. Okay. That's how we apply the chain rule to parametric equations. A really nice, easy method for finding the gradient of all sorts of different curves now, not just functions. But before you get going on the exercise, I just want to draw your attention to one potential hazard here, and it's to do with the second derivative. It would be really easy to think that d2y by dx squared, just following this pattern, is going to be d2y by dt squared divided by d2x by dt squared. And I would understand exactly why we would think that's the case. We would just follow on this idea of doing the reciprocal. But this is not true. Let's have a look at why. What does the second derivative with respect to x mean? Well, that means d by dx of dy by dx. But dy by dx is expressed in terms of t, like we have here. Dy by dx is a function of t. So instead, that's like differentiating with respect to t, but then multiplying by dt by dx, using the chain rule. Instead of differentiating with respect to x, I differentiate with respect to t, and then I kind of have this fractional cancelling out. That's how I remember this. D by dx, d by dx, the dt's cancel out. If you can't see that, maybe you can see the shadow. Cancel out like this, because we know these are not fractions. That's just a shortcut for helping us remember how the chain rule and these related rates are connected. So, that's enough of that. What's going on here? Well, we don't often write dt by dx. We're more familiar with dx by dt. We've used that in our previous questions here. So a more common form, and you will have to use this from time to time, is that the second derivative with respect to x is the same as d by dt of dy by dx. So take your expression for the gradient and then differentiate it with respect to t, and then divide it by dx by dt. If that's not clear enough way for you to write it, then write it as a horizontal fraction, d by dt of dy by dx divided by dx by dt. And that is your form for the second derivative. You can't just do this. Okay. I think that's given you more than you need to go through the contract questions for this exercise. As always, once you've finished, just answer the quick multiple choice question, and then let me know if there's anything in particular you want me to go through. Be very happy to do so. Good luck.